All right, so we're continuing with exercises from 13.5 and 13.6. So we're on page 868. We're going to do number 42. Which says in exercises 39 through 45, find the equation of the plane tangent to the given surface at the given point. So they give us y times e to the xy times e to the xy plus z squared equals 0. And they give us the point 0, -1, 1. So if you contrast this with problems 31 through 38, those particular problems you're given f of xy equals some function of x and y, of course, whereas here we have a function of x, y, and z equals some constant. So this is what I call a level surface, but I said you don't too much need to worry about that terminology. Just see that you have some function of x, y, and z equals a constant. So in this scenario, your normal vector to find your plane is going to be the gradient vector, where you're going to have f sub x, f sub y, and f sub z are your components of that vector. So the gradient of f of x, y, z equals, so the partial of this with respect to x, so y is a constant, so that's not going anywhere. The derivative of x times y with respect to x is y, so y is going to come out front as well. So we're going to have y squared times e to the xy. And then the partial of this with respect to y. So now we have a function of y times another function of y. So we're going to have to use the product rule there. So the derivative of y is just 1 times that stays the same, e to the xy, and then plus the y stays the same, and the derivative of e to the xy with respect to y is x times e to the xy. And then the partial of this with respect to z is just 2z. So this is how we would get our normal vector. We have to find our normal vector at that point. So n equals, we're putting in y equals -1, so we're going to get a 1 there, and then e to the 0, so we're just going to get 1. And here we're going to get e to the 0, which is 1, and then plus over here we're going to get 0 because of that x. We get 1 again, and then here 2z just gives us 2. So that's our normal vector. Just plug in this point into these, and now the equation of a plane is going to be this f sub x then times x minus x naught, so x minus 0 for us, and then 1 times y minus y naught, so plus 1 times y minus -1, or y plus 1, and then plus 2 times z minus z naught, plus 2 times z minus 1 equals 0. And that's the equation of the tangent plane to this level surface at that particular point. All right, so let's look at number 46 next. So number 46 says, find the point on the hyperbolic paraboloid z equals x squared minus 3y squared. So z equals x squared minus 3y squared, at which the tangent plane is parallel to the plane 8x equals 3y, 8x plus 3y minus z equals 4. So we're trying to find the points. We're looking for some point x comma y comma z where the tangent plane to this is parallel to the tangent plane, parallel to that plane that they gave us. So first, let's just look at this as which way do we approach finding our normal vector. We already have this set as z equals something, so it's different from this problem. What we do is we rewrite this so that we see negative z. So this is x squared minus 3y squared minus z equals 0. And now our f sub x, f sub y, and f sub z, our f sub z is going to be negative 1 here. So what is f sub x? Or actually, let's do this. So our n is going to be f sub x, f sub y, negative 1. And what is f sub x? F sub x is going to be 2x. F sub y is going to be negative 6y. And then f sub z would be negative 1, but we already have that. All right, so now this is normal to the plane tangent to z. I should use x naught. We'll just say x. I should use x naught y and the y naught, but we'll just say x, y, z. All right, so because we want this tangent plane to be parallel to that other plane, we want their normal vectors to be parallel to one another. So we want n to be parallel to the normal vector for that other plane, which was 8, 3, right? 8, 3, negative 1. So now what we're going to do is we're going to set this equal to some constant times that. We'll not just set them equal to one another. We have to parallel just means that this is equal to some constant like that. It's constant times that, excuse me. So solve 2x minus 6y negative 1 equals some constant c times 8, 3, negative 1. And now if we look at this, we equate corresponding components, but namely for us that because we're trying to solve for c first and foremost, so our k components, tell us that c has to be equal to 1. So I'll just write out all the equations. So this is 2x equals 8c, and then negative 6y equals 3c, and then negative 1 equals negative c. So this one tells us that c equals 1, and we take that and put it back in these, and we can solve for x and y. So that tells us with this c equals 1 that 2x equals 8, and that negative 6y equals 3. So this tells us that x equals 4, and this tells us y equals negative 1/2. All right, so we have the x and the y coordinate for the point that we're interested in. The last thing we need to do is find the z coordinate, and the way we do that is by taking this x and the y and plugging them back into this equation up here to find what the z is. So z is equal to 16 minus 3 times 1/4. So 16 minus 3/4, or 61/4. I'm sorry. So now our point that we were looking for is 4, comma, -1/2, comma, 61/4. So that's the point at which the tangent plane to this is parallel to that plane with this normal vector. All right, so let's look at another applied problem or word problem. So we'll look at number 64. So we're on page 869. Number 64, which says a metal plate with vertices 1, 1, 5, 1, 1, 3, and 5, 3 is heated by a flame at the origin, and the temperature at a point on the plate is inversely proportional to the distance from the origin. If an ant is located at the point 3, 2, in what direction should the ant crawl to cool the fastest? So our kind of hint as to where to start with this is the fact that it says we want this ant to cool the fastest really is kind of our clue here. And when we talked about most rapidly, we were talking about the gradient vector. So that's what we're looking at in this scenario. So let's start off with what is our function that we're considering to take the gradient vector of. So they tell us that it's a temperature function, and I'll read again. So the temperature at a point on the plate is inversely proportional to the distance from the origin. So when you see inversely proportional to, it's going to be K over whatever the other part of the description is. And that for us, they say inversely proportional to the distance from the origin. So the distance of a point X, comma, Y, the distance to the origin is the square root of, X squared plus Y squared. So that's the temperature function. Now, they also told us if the ant is located at the point 3, 2, in what direction should the ant crawl to cool the fastest? So they give us a region that we're considering 1, 1, some points. Just those are the corners of this particular plate, but that's just giving us some bounds for the problem. Those don't look like they're going to come into play at all for our computations, so we don't have to worry too much about those points that were given. So this is now K is not a value that we're going to find. Our answer is going to be in terms of K. So where K is a proportionality constant. All right, so cooling the fastest means, so because it's a temperature, cooling would be decreasing, means T of XY decreases most rapidly. Now we know the direction in which T of XY increases most rapidly, but we don't want the ant's temperature to increase. We want it to decrease, so we want it to be able to cool down. So it's going to go in the complete opposite direction of direction it would go if its temperature were to increase most rapidly, or the plate's temperature were to increase most rapidly. So T of XY increases most rapidly in the direction of the gradient t of xy. And let's just go ahead and compute that, which will be, so we need to take the partial of this with respect to x. The k, remember, that's just a constant, so we don't have to worry too much about that. So this is the same as x squared plus y squared raised to the negative 1/2. So when I'll write out the first one, then I'm going to simplify the second one. So it's going to be negative 1/2 times x squared plus y squared to the negative 3/2 times the derivative of the inside with respect to x, which is 2x, and then times our k, because that's not going anywhere, times k. Sorry, I should have put this on the next line, comma. Now when we take the partial with respect to y, it's going to be identical to this with the exception that's going to be a y. So those 2's are going to cancel. And in its simplified form, this will be, for the y's, will be k times y over, well, that's the negative sign, negative k times y over x squared plus y squared to the 3/2. Sorry, my components are on separate lines. So this would be the direction in which the temperature would increase most rapidly. So the ant should go in the opposite direction. So the ant should crawl in the opposite direction, which is going to be negative of that vector. And let's go ahead and put in our point, which was, sorry, I didn't write down the point. Point was 3, 2. It's not f, it's t. So scrap that. It is negative gradient of t at 3, 2. So now we're going to put 3, 2 into this. And when we put x equals 3, we're going to get negative 3k over, we are putting in x equals 2, so we have 9 there, and then plus the 4 gives us 13 to the 3/2. That's in the denominator. So 13 to the 3/2, comma. Now we are putting that same stuff in right here, and we're putting in y is 2, so negative 2k over 13 to the 3/2. All right, and I think that's all they wanted. In what direction should the ant crawl to cool the fastest? Yeah, the ant should crawl in the direction of this vector right here to cool the fastest. All right, so I'll stop this video here, and then we'll conclude sections 13.5 and 13.6 in our next video.